Hello. In this video, we finally apply all of those amazing skills of solving exponential and logarithmic equations to real-life examples, known as exponential growth and decay. Let's get started. So there are some very basic equations, which might not feel very basic, but they are essential that you know if you're an algebra student or going on in math. It's very important that you recognize how to set up a model which is representing exponential growth or decay. The most basic type of equation that we'll have, kind of like for a line, we have y equals mx plus b, right, slope-intercept form. For exponential growth or decay, we need to recognize that the output, we could call it y, we could call it a, amount, depending on time, equals your initial amount. Usually we use the subscript 0 for the original amount when time is 0. The original amount is your coefficient, times e, Euler's number, roughly 2.71, to the k, your growth or decay rate as a decimal. So for example, if you had a growth rate of 5%, k would be 0.05. If you have a decay rate of 7.5%, k would be negative 0.075. So we have the k decay rate or growth rate, and t is time. Traditionally it's in years, but it could be in hours, days, months, weeks, whatever they suggest. So we have this model that allows us to input data points, real life situation data points, into the model and create basically a prediction, right? We'll have a prediction for future points along the way. So that is the model that I highly recommend students commit to memory for exponential growth or decay. Another one that is helpful if you know 2 points already on the graph that's exponentially growing or falling is y equals a as your coefficient, kind of like a sub 0, and b as your base. It could be any number, not just e, and to the x power. This is really helpful if I give you 2 points like 2, 4, and then 3, and then we jump up to, let's say, 16. Something like this is happening. If we notice that we have exponential growth and we have 2 points that are given to us, we could then plug in the x and the y 2 times until we solve for a and b. So that's another model to keep in mind. Okay. So for now, we'll just keep the ones on the board that are already there. This is your most generalized model for exponential growth or decay. Again, if k is positive, we're talking about growth. So something like this is happening when k is positive. And if k is negative, we're talking about exponential decay. So something like that's happening. So noticing the difference, is k positive, is k negative, that's going to tell us something. Half-life is going to be important when we're talking about populations of substances or of humans or any type of population, animals, and we're wanting to know how long does it take for 1/2 of the original amount to remain. Now, if you're talking about medication, for example, if you take Tylenol or some other medication, how long would it take for that substance to only have half as much in your system? That would be called the half-life. And every sort of medication, every sort of radioactive material, every sort of population has a particular half-life if it's growing or falling exponentially, in this case falling. So when they talk about half-life, they are literally telling you how long it takes for half of the original amount, here's your original amount, for half of it to remain. So that's exponential decay. That's a code word. If I hear half-life, I know I'm talking about exponential decay. We're talking about that situation. Another thing that involves exponential growth, not just populations which could grow or decay, but banking. If you put money into a bank account, and if it's a savings account, for example, you should be earning some interest. It might not be very much, but some interest. Now, the bank will calculate that interest based on different models. They might compound it continuously, which is your best case scenario. Very rarely can you get this, though. That would be when your money is constantly being recalculated, your balance constantly updated, and they're recalculating and reaccruing new interest to your account. In that formula, it's very similar to our basic exponential growth or decay model. Instead of a sub 0, we use p for our initial amount that we've deposited. Now, this could also be the same model if you take out a loan on something. It's your initial principal, your initial balance, right? So it can either work for you or against you. Interest can. E is still Euler's number, roughly 2.71. R, instead of k, represents the rate at which you are growing, called your interest rate. So if you have an interest rate of 3%, R would be 0.03. And T is the amount of time, typically in years, that you allow your money to accrue interest, whether it's for you or against you. Okay, so what is the other model for banking? Well, what if your interest, instead of compounding every single second continuously using computers, what if they only do it maybe 3 times a year, or 4 times a year, or twice a year, or every week, etc.? They're going to give you words like annually. That would mean once a year, so n would be 1. Semi-annually means twice a year, every 6 months. So n equals 2. How many times per year? They have other words like quarterly. That's pretty popular with banks. I think most of my banks do it this way. That would be every quarter. Well, how many quarters are in a year? 4. Just like how many quarters are in a dollar? Same idea, 25%. Okay, so there's 4. That would mean every 3 months. And then you also have weekly. If you see that word, weekly, that's every week. There's 52 weeks in the year. Monthly, you know that's 12, right? 12 months in the year. Now the one that will be confusing, I want to make sure I put on here, is daily. Some students get daily confused with continuously. Continuously means literally every second it's recalculating, whereas daily means 1 time per day. So that would be how many days? Well, you might think that's going to be confusing. There's some years that have 365 days and other years that have 366 days. What are they going to do? Well, bankers like to be simple in this case, and they also like to cheat you out of some interest because they don't use 365, they don't use 366, instead they use 360. Why? Because on average, a month has roughly 30 days. 12 months times 30, roughly 360 days in the year. So they do cheat you out of 5 days of interest. If this is a mortgage or something, that means you have 5 days fewer of interest, so that's kind of nice. Okay. So if we're talking about any of these words, my money is compounding interest annually, semi-annually, daily, weekly. As soon as you see that adverb, right, that word after compounded, any one of those words, you know you're talking about this more complicated formula, where instead of base E in PERT that we use for continuous interest growth, we now have a base of 1 plus R over N, where 1 accounts for your initial principal, R accounts for your interest rate, N is accounting for how often they're going to recalculate it. So N is the number of times per year. And then your exponent is complicated. It's a product. It's N times T, the number of compoundings per year times the number of years. So it's basically the total number of compoundings. So how many times do they have to remultiply over and over again? Okay, so once you know which formula to use, you would have to apply it correctly and solve correctly for either the time it takes for this amount to accumulate, or for the interest rate that you need to use, or perhaps the principal that you need to deposit. So there's all kinds of things you could be asked to solve for, but logarithms are going to be helpful because we're solving exponential equations. So let's take a look at this example here and see if we can determine which model we need to play with. It says, for example, if $1,000, maybe your refund check, is deposited into an account paying 5% interest, we could determine how long it would take to accumulate $5,000 if the interest was compounded continuously. So there's lots of keywords here that help us figure out which formula, which model, which of these exponential models I'm using. What is the 1,000 representing? If you said P, you are correct. That's your initial principal that you deposit into the bank. What is 5%? If you said interest rate, that's correct, but I'd have to write it as a decimal, 0.05. What is the 5,000 representing? The accumulated amount, right? So the amount in total at the end, which would be our A. So A equals 5,000. And what is the word continuously, that adverb here after the word compounded? This is the key word that tells you which of those two formulas you're using. That's right, continuously tells me to use PERT. So I would have A equals principal times your E to the RT. So let's plug in what we have and see how to solve. We want to accumulate $5,000. So that's 5,000 on the left. We started off with $1,000, so that's P on the right. The base is E. The interest rate is provided for us. It's 5%, so R is the decimal, 0.05, and T is the amount of time we should allow our money to sit in the bank. So if I want to determine how long, which is T, it would take for this to happen, I need to solve for T. But where is T? It's in the exponent, which is why in our last video we learned how to solve exponential equations. What was our first step in solving an exponential equation? That's right, isolate the exponential part. A lot of students struggle with this. You have to first undo that multiplication with division. So if I divided 1,000 on both sides, I would now have 5 on the left. So watch your arithmetic. Little mistakes will cost us. 5 equals E to the 0.05 t. Now I have an exponential equation which I could solve with logarithms or by switching to logarithms. Either way of interpreting that gets you to the same place. Well, the natural log would make a lot of sense here. If I took a natural log on both sides, that allows me to do what? Bring down my power. Excellent. So on the left, I just have 5 as my argument. But on the right, what's my argument? That's right, e to the 0.05t. Now you could solve this two ways. You could recognize that I can bring down the entire exponent, 0.05, in front of ln(e). But if you did that, what is ln(e)? Do you remember this trick? Let me see if I can come over here. If I have a log base b of the same argument, what does that always equal? Do you remember? 1. Good job. So that applied to natural log as well. If I had the natural log of e, what must that equal? Well, that's a base e, isn't it? So natural log of e always equals 1. So with that fun fact in mind, I could recognize I have matching e right here. So this right side is really just the exponent, 0.05t. That's what I'm going to recommend we do instead of bringing down the power and then having 1 times 0.05t. It's the same thing. So let's go ahead and erase that part and just write 0.05t. Okay. So writing 0.05t here, this is where we're at. How would I now solve for t? How do you get t by itself? If you said undo multiplication with division, you're correct. So go ahead and carefully divide both sides by 0.05. That would mean t is now by itself, wouldn't it? So t equals the natural log of 5, close parentheses, divide by 0.05. When you do that, you should be getting approximately what number? Let's see what t should equal here. Did you get, as your answer in your calculator, roughly, here's my squiggle, roughly 32.189? If you did, that's the number of years, roughly, that you would need to let your $1,000 refund check sit in the bank account at 5% interest compounded continuously, which is very difficult to get. So assuming you have those nice interest rate and it's constantly recalculating interest, it would still take you 32 years at least in order for that money to become not $1,000, not $2,000, but $5,000. Now you might think that's a lot of time. I'm not going to want to do that. Just keep in mind, you didn't work for that money. It just sat there. So you got free money by letting it sit there. In life, if you're young, putting money into investments early is going to be the best thing you can do. Similarly, if you have a mortgage or a car note, something like that, if you can attack your principal early, that is going to save you a lot of money in the long run. So I highly recommend that you keep track of your investments when you're young, start early, and take off that debt little by little, because you're going to put yourself in a much better situation. Exponential growth works for you amazingly, but it also works against you amazingly. All right, let's take a look at our next example where we apply these formulas to another real-life situation. It says the number of bacteria in a culture, like a petri dish, at time t in hours obeys the law of uninhibited growth. We haven't mentioned this terminology before, but the law of uninhibited growth literally means the idea that you continue to grow forever at a doubling rate or at 3 times the rate or 4 times, maybe you're quadrupling each time. A law of uninhibited growth means that there's no carrying capacity, if you will. There's no asymptote that you're approaching. You continue growing forever. So when you see that, you should think exponential growth. That's what is the code word when we say law of uninhibited growth. Okay, so it has to follow some type of exponential growth model. They actually gave it to you here. That's very nice, but typically you'd create it yourself in a math or a science application using the data points that they give you, or using information that they've given you about key points in time. So in this situation, we know that the number in our petri dish, they're calling that n, depends on the time that the amount of bacteria has allowed to sit there. And so we notice that they say you start with 1,000 in your dish, and then your e is your base, and it's continuously growing exponentially. And so the interest rate here is going to be, not interest rate, I apologize, the growth rate is going to be k. K is 0.01. The formula that we're noticing is a of t equals our initial amount, a sub 0, e to the kt. Anytime you're talking about populations which are growing or decaying exponentially, that's the model to use. So they've given me a new name for it. Instead of a for amount, n for number. Okay. Instead of a sub 0, they've told me the initial amount right here. 1,000 is my initial amount. The reason for that, by the way, it's not just made up. If you were to let time t equal 0, you would say, okay, initially when time t is 0, how many bacteria do I have in my culture? N of 0, if you will. Well, wouldn't that just be 1,000 times e to the 0.01 times 0? But what happens if you multiply by 0? You get 0. So I would just have e to the 0 here as your exponent. If this exponent is a 0, what does it mean to take anything to the 0 power? Well, it really means you're multiplying by 1, right? So you'd have 1 times 1,000, which brings us back to 1,000. So the initial amount when time is 0 is 1,000. That's why the equation says that coefficient is always your initial amount. Okay, so now we can answer the first couple questions, hopefully easily. Feel free to do so yourself and then check your answer. It says in A, how many bacteria were present originally? We just answered that, didn't we? That is your initial amount. So A of 0 equals 1,000. So there were 1,000 bacteria originally in our Petri dish. What is the growth rate? Well, we know it's not decaying, right? Because this is a law of uninhibited growth. So our K should be positive. And K is represented as the coefficient of T in this model. So it's the number right here, 0.01. But how do we write that as a percentage? Just 1%. Move that decimal 2 places to the right. So we have 1% growth rate for this bacteria. That's kind of a big deal, but not terribly huge. How many bacteria will there be after 4 hours? That's a pretty basic equation, right? Where we just are given the time. We know the model, the number of bacteria in the dish, depends on time. So in this case, they're giving you 4. You're simply plugging in 1,000 times e to the 0.01, replacing t with 4. So this is a more foundational type of problem where they're just checking if you can plug something into your calculator, and hopefully you can do that correctly. The main thing students often do incorrectly and get the wrong answer is if they forget their parentheses, or if they forget to realize you have to multiply in the exponent first and then raise e to that power. So it's e to the power of this product. Whenever you get that, multiply the result by 1,000. And the answer should be approximately 1,040, I think 0.811. And they'll tell you word around usually in your problems. They might say to the nearest whole number, which would be 1,041, or they might say to the nearest decimal or 3 decimals or something like this. Okay, so we know that after 4 hours, we've grown by over 40 bacteria, right? So it is growing quickly, maybe not as quickly as you thought it would, but it's quickly. When will the bacteria reach 1,700? Now this requires more of our new skills that we've been working on in this class. So let's see what this means. If the population reaches 1,700, where should I plug that number into my model? If you said for t, not quite right, because t is the amount of time that's gone by in years. 1,700 is not time. What is 1,700? It's bacteria, right? It's the number of bacteria. So that would need to go on the left side as your output of the model, right? Your output depends on the time, which is your input. So if I put my output at 1,700 bacteria, we're looking for what input, what time would make that happen. How long would it take for this to occur? Well, that should equal the other side, 1,000 e to the 0.01 t. This is very similar to our last example on the first slide, so feel free to pause and go back and check yourself by yourself, see if you can do this on your own. Okay, let's see how you did. What was the first thing you did if you're trying to solve for t? Did you say divide by 1,000? If so, that's correct. You have to isolate the exponential part. So if that's something that you're not sure about, make sure you put that in your notes and drill that into yourself. If I'm solving an exponential equation, I first isolate the exponential part. So to do that, I undo multiplication here. This becomes 1,700 divided by 1,000. That's just the decimal 1.7, if you like decimals, equaling e to the 0.01 t. And then what did we do? What did you do? If you said, I'm going to take the natural log of both sides, you are correct. The natural log of 1.7 must equal, and if I take the natural log of e to the 0.01 t, there was a little shortcut we talked about, right? They have the same base here. What happens if they have the same base matching like that? That's right, you just get the exponent. So this should just become 0.01 t. So let's erase that. And what was your final step now to get t by itself? Did you undo multiplication with division? If so, you would get t equals the natural log of 1.7 in parentheses divided by 0.01. That would be your exact answer prior to putting it in your calculator. Once you put it in your calculator, you should be getting roughly 53.063. And this was time in hours, right? So that's a little bit over 2 days. 48 hours is 2 days. So a little bit over 2 days, your initial population of 1,000 bacteria has now grown to 1,700. So exponential growth, it happens pretty quickly. It's happening very, very quickly. Okay, so we've done one example where you had to solve for time. Let's see if you can apply this to the last example. It's a little more complicated, but use your thinking caps. You can do this. Example 2, let's talk about a substance that's radioactive, like iodine-131. It's known that iodine-131 has a model of decay that is represented by this equation. A of T equals 100 e to the negative 0.087 T, where the amount is measured in grams, the amount of the substance. Okay, so then they tell me in part A, they want to know what the decay rate is. So see if you can take apart the equation and answer that question. Did you see, well, that's actually my K as a percentage, right? What is your K? Negative 0.087 is my K. So if you recognize negative 0.087 is K, then what is my decay rate as a percentage? When they ask you for a decay rate or a growth rate, they're looking for a percentage. Well, moving your decimal 2 places, that's really 8.7% rate of decay. Notice I don't need to put the negative sign in front because I'm telling the reader that's the rate of decay, right? If I said the rate of growth, then it would have been the positive K value. The second question they ask you is, how much iodine-131 remains after 9 days? So where would 9 go in this model? Is 9 your time or is it your amount? It would be your time. Good job. This is your T. So they're really asking you to find A of 9. So this is again a matter of just plugging into your technology correctly. 100 times e to the negative 0.087 times your time, which is 9. Again, be sure to do that carefully. Get your multiplication and your exponent first. Raise e to that power. Multiply that result by 100. If you do this correctly and carefully, you should be getting approximately 45.703. See if that's what you got. If you're having any calculator issues, you know you can talk to me. Email me, come see me. Definitely want to make sure you are set. Okay, the next question requires a little more thinking. They're asking you to determine the half-life. Now, don't Google it. I know you could find out the half-life for the substance by just Googling it, but I would like for you to try to do it yourself. What does it mean to find the half-life? Are they looking for time or are they looking for an amount? Time, right? The time it takes for half of the amount to be remaining. So I need T. If they ask you for half-life, you need to find T when half of the original amount, which is A sub 0, right? When half of the original amount is left or it remains. So how would I set this up? If I need to find T, the time it takes for half of the original amount A sub 0 to remain. Well, that would mean that the remaining amount, A of T, in my model is half of the original amount, right? So I could write on the left side, half or 0.5 of means multiply the original amount. That should be my remainder, right? That should be the amount that's left after the time, after the half-life. Equals my 100, my initial amount. So I could replace A sub 0 here if you're paying close attention. They gave you A sub 0, didn't they? That was 100. A sub 0 was 100. So you are welcome to put in that number right now if you like. Okay. If you put in the initial amount, we're really saying how long before I just have 50 grams, right? Because that is a half of 100. So this just becomes 50 in this case, equaling the other side of the model, which was 100 e to the negative 0.087 t. So I have 100 e to the negative 0.087 t equaling 50. Okay, what did we do next typically? We isolated the exponential part. Good job. So how did I do that? I divided by a 50 by 100, by the number touching the exponential. If I do that, look what happens. It's not a coincidence. 50 divided by 100 is 5 over 10, or 1 over 2. 1/2. Interesting. If you're wondering, Professor, is that always going to happen when I'm dealing with half-life? I'm looking for half-life? The answer is yes, because it didn't matter what the initial amount was here and here, right? You're going to divide by 100. That initial amount goes away. You just get half every time. So when you're solving a half-life problem, if you're looking for half-life, you could start out by just saying 1/2 equals e to my decay rate times t. It's a nice shortcut. It doesn't hurt to go through the process, though, of where it comes from, so you truly understand it. At this point, how did we solve for t, just like we did in our last couple examples? That's right, we took a natural log of both sides, natural log of 0.5, or half, equaling, and if I take a natural log of e to some power, what is the result? Just the power, good job. Negative 0.087t will be the result of taking the natural log of that side. Finally, how would you get t? How would you get this half-life here? Yeah, that's right, you would divide by whatever is touching t. So t should equal the natural log of 0.5 divided by negative 0.087. Now that again, that pattern will always hold if you're finding half-life. So if you want a shortcut, it will always equal the natural log of 0.5 over your decay rate as a decimal. That's definitely going to hold, but understanding the process is going to be helpful going forward to more complicated situations. So it looks like T approximates to roughly 7.967, where at this time T was in days, it looks like. So this is how many days would need to go by for half of the substance to go away, right? That's not too bad, right? Sometimes half-life for some radioactive substances is in the years, right? 20 years, 30 years, hundreds of years. So if you just have to wait 8 days roughly for half the substance to go away, that's not really terrible. Okay, but if this was medication, that would be a little bit strong, wouldn't it? Usually medication has like in hours, maybe 8 hours or 12 hours, something like this for its half-life. Okay, so what about the last question? See if you can set that one up yourself. When will just 70 grams remain? Now, some students are a little bit clever here. They go, okay, well, if I know that every 9 days, half of it is left, I'm just going to keep going, right? I'm going to say, okay, well, it took me it was 8 days. It took me 8 days to drop from 100 to 50. I'm going to back up, and maybe I'm going to say it's around 6 days, something like that. Okay, you might have a gut feeling, but I need you to be able to solve it exactly. So how would you go about setting this up? Okay, so we want 70 grams to remain, so where would 70 go? If you said it would go here for the amount, you would be correct. So 70 should be equal to 100 e to the negative 0.087 t. Can you recognize that that equation is exactly the same type as the equation we just did? A number equals another number, e to a power. Same thing. So take a moment and try it yourself if you haven't already done so. Okay, did you divide by 100? Good. You wanted to isolate first? So 70 divided by 100 is 7 over 10, or the decimal 0.7. And that should equal e to the negative 0.087 t. What did you do now? Just like last time? Yep, you took the natural log on both sides. In the end, you should be getting t equals the natural log of 0.7 divided by the decay rate, negative 0.087. And the final result of that would be around roughly 4.0997. So around 4.0997, a little over 4 days. If you said 6, you were a little bit off, right? It was a little over 4 days for 100 grams of the substance to now be down to 70. And you could solve for any number. And I would encourage you to try your own numbers and maybe even use Desmos.com or your graphing calculator to track it, to visually see the decay that is exponential in this model and understand not only how to solve it, but to interpret it from the graph. Okay, so we've talked today about how to apply solving exponential functions to exponential growth and decay. Make sure that you memorize the appropriate equations and practice recognizing when to use each one. And if you have any questions, let me know. But be sure to practice, because math is not a spectator sport. I'll see you next time.